we need to be able to measure magnetic fields, and the Hall probe is a clever little device for doing just that. In this lesson video, we're going to look at how it's designed, we're going to look at how the Hall voltage is generated, we're going to look at how we can calculate the magnetic field strength from the Hall voltage, and we're going to look at a curious little effect due to the semiconductor design of the Hall probe. So let's get started. Actually, before that, you might want to stop and look back at how the drift velocity formula, I equals nave, was derived, as we're going to build on that later. So hopefully you review that and we can start. Now, let's start off by considering a metal plate with thickness T. The plate is in a magnetic field going upwards through the plate. I'm going to use a cell to drive a current I along the length of the plate. So, what happens next? What happens to the current as it goes through the magnetic field? Hopefully that thinking time was enough. The current will experience a force. The left-hand rule tells us the direction of the force. First finger field is up. Second finger current is left to right. Thumb is thrust, so towards the front face of the metal plate. The current experiences a force towards the front face. Now let's shift our perspective. Let's look top down. The current is going left to right, but it's also pushed downwards. We could say there is a vertical component to the movement of the charge. So we could say there is a current downwards. This means there is a potential difference between the top and bottom in this diagram. Or, back to the original diagram, between the back and the front faces. This is the Hall voltage. The stronger the magnetic field, the more the charge carriers are deflected and the larger the Hall voltage. This means that all we need to do to measure the strength of the magnetic field is to set up this circuit and measure the potential difference between these two edges. We do need an equation as well though, that relates the Hall voltage, VH, to the magnetic flux density, B. And this is the equation, VH equals BI over NTQ. So, let's derive it. Actually, pause the video and give it a go. Remember, go back and review the derivation of the drift velocity equation, because not only is that a useful activity, it might save you a bit of time and give you some clues. Alright, so hopefully you've given that a go. You should recall that the defining equation for an electric field is E equals F over Q. More usefully though, E equals V over D, giving F over Q equals V over D, or F equals VQ over D. For a charge carrier with charge small q, that's F equals VQ over D. We also know that the force due to a magnetic field is given by F equals BQV. Now remember, that's small v there for velocity. If these forces are equal, that gives VQ over D equals BQV, where d is the width of the plate. Making big V the subject, we get V equals BQVD over Q. Now it would be tempting right now to get rid of Q, but we're not going to yet because we're going to find it useful. What we're going to do instead is bring in I equals NAVE, or rather in this case I equals NAVQ. So Q equals I over NAV. Substituting this into the top Q, we get V equals BIVD over QNAV. So now we can cancel out the velocity, and that gives us V equals BID over QNA. Finishing off, area is length times height, so A equals dt, meaning d over A equals 1 over t, giving us V equals BI over QNT. Right, so that was pretty long. It's also an odd route, but we got somewhere useful. Using this equation and designing the Hall probe, we can measure I. We also know Q, N and T because we designed the thing. So if we keep those things constant, we find that VH is proportional to B. And that makes this a very useful device. There is one more thing to consider though, and that is what to make the Hall probe out of. Metal seems the most obvious, but have a think about it. In fact, consider these 4 changes and compare them with my original here. What will be the effect on the magnitude of the Hall voltage and the direction, the sign of the Hall voltage, if we change the direction of the current? What will be the effect on the magnitude of the Hall voltage and the direction of the Hall voltage if we change the direction of the magnetic field? So the current is going left to right, the field is going top to bottom now. What will be the effect on the magnitude of the Hall voltage and the direction of the Hall voltage if we keep the current left to right and the field bottom to top like the diagram, but change the material to an N-type semiconductor? And what will be the effect on the magnitude of the Hall voltage and the direction of the Hall voltage if we keep the current left to right and the field bottom to top like the diagram, but this time change the material to a P-type semiconductor? In fact, that's such a good question that I'm going to save the answer for another video. So have a really good think about it. Remember, this is a good question. To be able to actually understand what's happening is going to need some really good thinking. So have a good think and try to write down your answer with reason.